Yeah, it does suck. It does suck, and I've never been able to go back and and do stupid things and have an excuse of being young. Okay, we have two unresolved issues from last class. Last class was kind of a little bit of a debacle there at the end. And I thought about, I don't like to leave classes the way we left class, but I thought about it and I was like, okay, how do we handle this? So the point of me bringing the last example, see, I was supposed to show you this example in class. It was this one right here. I decided not to do this one. It was find the volume of the largest rectangular box with edges parallel to the axis that can be inscribed in an ellipsoid. And I decided instead to talk about a cone inside of a sphere. The whole reason I do this problem in 11.7 is because when we start to set it up, we start to realize very quickly just how crappy that is going to be, all right? And what we do is I normally set it up and I go, do we really want to do this? I mean, we realize what we would have to do here. The algebra is a nightmare. And I could spend about 30 to 45 minutes going through that problem. And then, after that, we get to 11.8. And when I do 11.8, at the very end of this section, I think it's in here. No. Well, there's word problems very similar to the ones that I ended 11.7 with. In fact, I like to do the problem from 11.7 in this section 11.8 because when we do it, it's like pretty straightforward and pretty clean. In other words, I try and get you to appreciate the value of this section 11.8. So what I've decided to do is leave these still as unresolved, give you a new tool to use, and then we can decide whether or not we want to attack these with this new tool. All right? Does that sound fair? Okay. So Lagrange multipliers. This section is one of my favorites because it's just such a powerful result that we have from the Lagrange multipliers method. This is a method. It's going to look very strange when I put it up here. I'm going to try and show you a geometric rationale for this method. I'll do my best, all right? Because as a student, I did not understand why this all works. So I tried to come up with a geometric rationale for it, and I'll show it to you. All right, so what we learned in 11.7 were two different topics. We said that if we have a function of two variables, we can find the local maximums and minimums and saddles of that function, and that we use the capital D. We calculated capital D to do that. And that was just looking for local max, mins, and saddles on the function's implied domain. Now, in the second part, we were trying to find the absolute max and mins of a function on a closed bounded region. That's where you had to like travel around the edges and you had to check on the inside and you compare the points. So those were the two things. We now develop a very powerful method for finding the maximum and minimum values of a function subject to a constraint. Now, this subject to a constraint may sound weird, like what do I mean subject to a constraint? But we've already done this. When we were on a closed bounded region, we were subjecting our function to some sort of constraint. And this method works for pretty much any constraint that you can come up with. So here's the actual method. And like I said, it's going to look really weird. All right. The method of Lagrange multipliers. Right now we're going to look at this method for just a function of two variables. And this is also what makes this method so powerful, is that, you know, when we were calculating D and the method that we did last class, that only works when you have a function of two variables, all right? Only with two variables. The Lagrange multipliers method works for a function of two or more variables. And so it is more powerful than what we had before. So we'll start, though, with two variables. Let's say we're given a function f of xy, and we subject it to some constraint. So this constraint right here is any equation that you can come up with that has x and y in it. Remember, our function depends on x and y, but we have an equation that is somehow restricting the x's and the y's that we're allowed to plug in. That's our constraint equation. Then what we do is the following. To find the maximum and minimum values of the function f, we will do these two things. First, find all the values of x, y, and lambda such that the following two equations are true. So what we're going to have to do is set up sets of equations and solve them. And here's the equations we have to set up. We have to take the gradient of f and set it equal to lambda, which is a constant. So look at lambda as just some arbitrary letter. We have to find out what it is. But some constant times the gradient of g. Now, remember, the constraint, we have a constraint equation, which is some function of x and y equal to some constant k. If we look at the left side of this equation, the part that has the x's and the y's in it, and we take that and look at it as a function of two variables, then we're somehow trying to figure out where these two are equal, right? What is the gradient? It's the partials, yes, but like object-wise, what is a gradient? Is it a number? It's a vector, right? The gradient is a vector, all right? And so we're trying to figure out where this vector, which is the gradient of f, where it's equal to some constant times the gradient of g. And that's a vector also. So we're actually trying to figure out where these two vectors are parallel, right? Because remember what it meant for two vectors to be parallel? It meant that they're scalar multiples of one another. And that's exactly what this is saying. We have to figure out what lambda, what constant, makes the two gradients parallel. But why does that tell us where we have a max and min? That's why I'm going to bring in the visual here in a second. And then we also have to make sure that while we're trying to solve the x, y, and lambda, we need to make sure that we always maintain the equality of the constraint. This equation must always hold for whatever values of x, y, and lambda we find. I know this sounds weird in the beginning, just hang tight, all right? We're going to do a problem. All right, once we figure out all the x, y's, and lambdas, because there might be more than one x, might be more than one y, might be more than one lambda. Once we find all of them, then what we're going to do is evaluate our function f at all those x's and y's that we find, and then the largest is the max and the smallest is the min. All right, that's the method. For two variables, that's the method. Now, let's try and understand visually why. And this is the part that's really, you're either going to see it or you're not. All right, I have a surface here, all right? Y'all know what that's called? Cone is pointed. This one's, it's a paraboloid. Okay, this is a paraboloid. It's kind of like a bowl, right? We've got some sort of bowl here. All right, right now, would you agree that this surface, if I were allowed to keep going up, has no maximum, right? It does have a minimum?
Yes.
Okay, we could probably find that minimum by calculating capital D, right? It would give us like a local minimum. All right, that's just our function without any constraints. Just let the function be. Now what I'm going to do is I'm going to restrict this function to some constraint. And I'm just making one up. Where's my constraint? Oh, why didn't it show up over here? Oh, because I clicked the wrong thing. Sorry. Here's my constraint. There it is. Okay, so what I'm doing is this is my domain, okay? The points that I'm going to plug into the surface, which is really on the ground over here. If I constrain my function to just this right here, then it would just map those points up into my surface, and I'd have that ring that's up there on the function, right? And I'm trying to figure out where I'm going to have maximums or mins on that green piece. Let me keep going here. Let me show you what the gradient of G looks like. The gradient of G is always orthogonal to the curve. Okay, that's one of the properties of our gradient vector. It gives us our steepest descent, right? Remember the gradient gives us our steepest descent? So let me see if I can spin this over here. Can you all see it there? Oh, there it is. Okay, you can see it better there. So if I were standing on this curve, on that green, and I wanted to head in a direction that I would go up the fastest, I would head directly away from the green curve, and that would move me up the surface as fast as possible. Do you all agree? Yeah? Okay. That's the gradient of G. Now let me show you the gradient. Hold on. There's that blue part. Do you see the blue part there? That doesn't look like it's landing on my curve. Hold on a second. Where is my... Oh, shit. Let me bring this out of here. Okay, I had the wrong function up there. I apologize. That's our F curve. So do you see the green being mapped up to this curve right here? The blue, if we take these points in green and map them up into the function, we get the blue part. All right? Not this green part. We get the blue. Is that all right? Okay. Now the gradient vector of G, all I've done is I've moved this ring up here just so you can see where that ring is relative to the blue. All right? We're trying to find the highest and lowest points on the blue curve. Here's my constraint. I know the gradient of G is right here. It's pointing away from the center of that circle. Now, let's look at our maximum and minimum points. Okay, you see our maxes are right up there, and our mins are down there. What I'm going to do now is I'm going to move around my constraint. Okay, I'm moving my constraint here, right? Moving around it, and I've also put on here the gradient of F. And it's hard to see. Okay, so do y'all see the gradient of F there? Do y'all see that blue vector? Okay, I'm going to move back to a different place on the curve. Okay, right there. Let's just take a look. If I am at this point right here, and I plug that into the function, I'm going to be right up here. It's hard to see it, but I'm right there. And if I look at the gradient of F and the gradient of G, the gradient of the blue and the green, notice that these two vectors are not parallel. Do y'all see that? And if I move around, as I move around, at what points are they parallel? So you can see it looks like they correspond to, like if I'm right, get back there. There, okay? If I'm right there, where am I on this surface? At the minimum, right? And then if I move up here, look, they're parallel there, aren't they? And notice where I am? At a maximum. Now this is not a proof, okay? This is just to show you that the reason why Lagrange multipliers works is because when we're at a maximum, these gradient vectors become parallel. It's just to try and give you some idea of why we're doing the calculation.
That goes into the critical points that we care about.
That's right. It gives us, this is a new way to calculate critical points. It's by finding where the gradient vector of F and the gradient vector of G are parallel. All right, let's do an example. All right, oh, wait, before, I have to break this down a little bit. Remember the gradient of F is a vector, right? So if we look at that equation, part one, if we break it down, the gradient of F being equal to lambda times the gradient of G means the partial of F with respect to X, partial of F with respect to Y, this is our gradient vector of F, must be equal to lambda times the gradient vector of g. And the gradient vector of g is the two partials again, right, with lambda distributed through. Now, for two vectors to be equal, their components have to be equal. So that means I'm going to set the first component equal to the first component, second component to second component, and I come up with these two equations, don't I? And then we have the second part, which is the constraint equation that has to be true. So in total, what we get are, whenever we're trying to find the maximum and minimum values of a function of two variables using the Lagrange multipliers method, we are going to wind up having to solve simultaneously a system of three equations. Very key here, system of three equations. These equations do not have to be linear equations. So you may not use Gaussian elimination or matrices. You can't do that because these equations are not necessarily linear. Do you understand? And because of that, it's going to be a little bit problematic, as you're going to see. There's going to be a lot of algebra that we're going to have to go through to make sure we get these solutions. One of the big things I want you to take note of right now when I do this first example is that as I work through it, I'm going to constantly be trying to keep track of different scenarios, like case 1, case 2, case 3, because as you'll see, we're going to have different, we're going to say x can be 0 or x can be 2. And then we have to say, okay, well, if x is 0, all this stuff happens. And then we have to go back and say, well, what if x was 2? Oh, well, then all this stuff would happen. So we have to keep track of all the different scenarios that we have. All right, let's see this in action. Find the maximum and minimum of the function f of x equals x squared plus 2y squared on x squared plus y squared equals 1. So we have this paraboloid. This is actually the one I showed you just a second ago. We are going to restrict its domain to this curve down here on the ground, which is x squared plus y squared equals 1. Do y'all see the constraint equation? It's right there. See our function? Yes? So what happens if we take just these blue points, throw them into the function, we get that curve, right? Oh, wow, I even shaded it so you could see it went up there. Okay, so there's our blue curve, right? And we're trying to figure out the maximum and minimum points on that curve, which are those right there, right? That's visually what we're trying to do. So how do we do it? Let's do it. First, let's identify what is f, what's f of xy, what's g of xy. So what is f of xy here? It's given, right? So there's no magic happening there. Okay, now let's write down the constraint equation. The constraint equation is x squared plus y squared equals 1, which means this is our g of xy, and then this is k, right? Equals k. With me? All right, first step, we're going to set up three equations right now. It becomes very difficult for me to get this all on the board, so I'm going to have to keep erasing. So take good notes. All right. Let's go ahead and find out what the gradient of f is. What is the gradient of f? The vector 2x, comma 4y, okay. Let's go ahead and find out what the gradient of g is. It's the vector 2x, 2y, all right? And that's all the information I need to go ahead and begin the method. So now I'm going to establish my three equations. Equation 1, equation 2, and equation 3. Here they are. My first equation is 2x equals lambda 2x. So all I'm doing is I'm setting the first component of f equal to the first component of g, but I have to say times lambda on g. So that's our first equation. Second equation, 4y equals lambda times 2y, right? And then the last equation is the constraint equation. Good. X squared plus y squared equals 1. Have any of you ever seen, I mean, unless you've maybe taken this class before, have any of you seen in any of your other classes the method of Lagrange multipliers before? No? Maybe? Okay. I know when I was taking calculus, it's the first time I'd ever seen this at all. So, all right, we need to figure out, we need to find right now an x, a y, and a lambda that make all three of these true at the same time. That's our goal. All right? We might have more than one. We need to find them all. How many should we have? Look, think back to that picture. We should have 4. There should be 4 sets of x, y, and lambdas that make all of these true at one time. So at this point, with these equations, it's my pleasure to now figure out what they are, and I can work with these equations however I want. So let me start messing around with some things here. What could I do with that first equation? I could divide by 2x. Could I? Okay, this is one of those big, like, oh shit, I never realized that I need to be careful with that. This right here is major danger zone right here. This is major, major, major danger zone. Because if you do this, this will be 1, right? And this will be lambda, so lambda's 1. But what you've done there is you've said to me, what? I mean, you can't just cancel those without telling me something. X can't be 0. You must right there be very clear that x can't be 0, because the only way you can divide both sides by x is if you guarantee me x can't be 0, right? Because then you'd have division by 0. That's a very subtle thing that we never really talk about too much in algebra. Hopefully your teacher did. I know I do in mine. That is not recommended to divide through. So never divide both sides of an equation by a variable unless you have no choice. If you do, you better make sure you look at and state this. Because what this is, if you do it this way, what this means is, yes, lambda's 1. I'm okay with you doing that. But you're going to need to go back and talk about these 3 equations if x was 0. Then what can you say? So we'd have to take these 2 scenarios. Here, x isn't 0, lambda's 1. But if x was 0, what would happen? So instead of doing this, we just write the equation down. So I'm going to try and be pretty good with this. Equation 1 states that 2x equals 2x times lambda. I just rearranged it. I'm going to rearrange this equation by subtracting. Now you can subtract 2x lambda from both sides. That's okay, right? And then what? Factor out a 2x. That is the preferred way to do this. 2x, you're left with 1 minus lambda equals 0. And then what are your 2 solutions? 2 factors. So you set them both equal to 0. You get x is 0 and lambda is 1. Okay. And you know what I'm going to do? I've never done this before, but let's just kind of like up here, I'm going to just put up here A, okay, and just underline this. This is all within my A thinking. And then later on I might have a different thought, and that's going to be all my B thinking, all right? So right now all I did is took the first equation, solved it, and when I do that, the only way to make that first equation true is to make x equal to 0 and lambda equal to 1, all right? Well, we have to continue to work with those 2 ideas. So which one do you want to start with? You want to do lambda equals 1? Okay. So still continuing this. If lambda equals 1, then what can you tell me? Then what? Where you get, well, yes, but that was working with this equation. That's where we got lambda being 1 from. What can you tell me from the second equation? Equation 2 implies that 4y must equal 2y. Do you all see that? If lambda's 1, then this equation now says that 4y must be 2y. And let's subtract 2y from both sides. What would that tell you? 2y equals 0, and that means y must be 0. Right? And now if y is 0, what can you tell me? you can go to this equation and tell me what x is, right? So if y is 0, then equation 3 implies that x squared equals 1, right? Because y is 0. So that means that x is equal to plus or minus 1. Square root of both sides, right? All right. We've got some candidates here, don't we? Yes.
So when we look at the lambda equals 1, we just completely ignore that we found x equals 0?
I haven't done that yet. I'm going to come back to it. But I'm glad you brought that up, because that's what I was about to say right now is, right now, as we have considered equation 1. Equation 1, the only way it can be true is if one of these two things is true. So what we did is we said, okay, let's take the lambda. What if the lambda is 1? If the lambda is 1, that forces y to be 0. And if y is 0, that forces x to be plus or minus 1. So here's what I've got from this idea. From lambda being 1, I have everything in here goes with lambda being 1, right? So I could say, if I want just out here to remind myself, this lambda 1 corresponds to everything there, right? And what was my result? That x would have to be plus or minus 1, y would have to be 0. That would be my x and y, right? And I'd be done? We normally put on the outside what the lambda is. So we usually do x, y, and lambda. Now you're only going to use the x and y when you plug into the function, but this way, if you write it like this, it shows all your x's, y's, and lambdas together, so you know how they all correspond to one another. Does that make sense? Any questions? I've got 2 points, right? There should be 4. Okay, let's go get the others. So what do you think I'm going to do now? I'm going to suppose x is 0, right? Yeah, I'm going to suppose that x is 0. So now, let's do everything again. This time I'm going to say this case right here, right? If x is 0, then what can you tell me? Equation 3 tells us that y squared equals 1, which implies that y must be equal to plus or minus 1. Now, what about lambda, though? And we don't need lambda, okay? But could we get lambda from this? If I know what y is, right? Because look, if x is 0, look at this first equation. If x is 0, lambda doesn't matter, does it? You can give me any lambda, it's going to go away. But if I turn out to say that y is 1 or negative 1, then I'm going to be able to solve for lambda, right? So what happens if y is 1? I'm indenting this because it's within the same thought here. If y equals 1, what does equation 2 tell me? That lambda is, so that would be 4 equals 2 lambda, which implies that lambda is 2. Right? And then what if y is negative 1? If y is negative 1, equation 2 would tell us that negative 4 equals what? Negative 2 lambda, which would mean what? Lambda is 2 also. So all of this is happening within the idea that x was 0, right? So now I have some other points. Let's write them down. Here's my little summary over here. I had that when x was 0, what would y be? Plus or minus 1. And the lambda didn't change, did it? Plus or minus 1, and then my lambda would have been just 2. In both of these cases, right? For positive 1 or negative 1, my lambda would have been 2. Well, are we done? We found 4, right? But you knew that to start the problem because I gave you a picture, right? So we know we're done, but how would we know we're done had we not had the picture?
You have to test for y.
We have to make sure there's nothing else that works. This is the biggest issue with Lagrange, is like knowing when you're done and knowing if you've exhausted all the different possibilities. So we've worked with the first equation, right? We've worked with the first equation and we've exhausted both of those possibilities. Let's go take a look at the second equation and see if there's any possibilities that we have not exhausted. You ready to look at the second equation? Of course you are. I'll call this B. This is all within our thought, our second thought here. I'm going to start with equation 2, and I'm going to write down 4y equals lambda times 2y. Now I can do the same thing I just did a second ago, right? Move everything to one side, and I could get 4y minus 2y lambda or 2 lambda y, doesn't matter, equals 0. Then I could factor out a 2y and be left with 2 minus lambda, and that would give me two things. Y is 0 or lambda is 2. Now, do I need to look at y equals 0?
No.
I already know what would happen. If y is 0, x is plus or minus 1. I already have this scenario taken care of, don't I? What if lambda is 2? I already have that scenario. When lambda is 2, I have this already covered, don't I? So I have exhausted these two scenarios already, so I don't need to consider them.
Would you have to go to equation 3?
We could look at equation 3, right? But the problem with equation 3, yes, sorry?
Did we test the equation when lambda was 2? Yes.
We didn't test it. We got lambda equals 2. We know when lambda is 2. It happens when x is 0 and y is 1, right?
Okay.
So when we're looking over here, if your lambda is 2, then we've already looked at that scenario. I mean, this is the only way lambda can be 2, is if this happens. Okay? Now, equation 3, if we write that down, there's really nothing we're going to be able to gain from it, because equation 3 by itself is a circle. And there's an infinite number of points that satisfy that, right? So there's nothing, I mean, we can't go check every one of them. So this is it. I mean, we're done at this point. So you're never going to write equation 3 down by itself and then go try and find critical points from it. You won't do that with your constraint equation. You will use your constraint equation to try and nail down certain values, but you won't ever start with equation 3 and just start asking for solutions. Okay? Yes?
Equation 3 is always going to be a circle?
No. No, equation 3 is not always a circle.
Will we ever be able to gain something from equation 3?
Well, we gained from equation 3 right here. Remember when x was 0, didn't we use equation 3 to get y? Right? So we will use it, definitely. Just not as your initial starting. Okay, so now what would we do? We have 4 points. You would do what now? Plug them back into the original function. So you now have to evaluate your function. So you're going to now test and compare here. You need to do f of 1, 0. You need to do f of negative 1, 0. You need to do f of 0, 1, and f of 0, negative 1. You compare all these answers. F of 1, 0, 1. F of negative 1, 0, 1. F of 0, 1 is 2, and 0, negative 1 is 2. So you had a maximum value of 2. It occurred at 2 different points, right? A minimum value of 1. It occurred at 2 different points. I do not enjoy grading these problems. Yeah, can you imagine? Yeah, it's hard to follow people's thoughts, which is why I encourage you to try and become organized with your thoughts and write down properly. Communicating them to me. find the maximum and minimum of f of x equals 4x plus 6y, subject to another circular constraint. Every one of the problems I'm going to show you today has a slightly different sort of algebraic approach when you're trying to find x, y, and lambda. All right, let's see if we can set up the three equations without having to write all that other junk down. We have equation 1, equation 2, and then equation 3. What is equation 1? 4 equals lambda times what? 2x. So you're taking the partial of f with respect to x, which is 4. You're setting it equal to the partial of g with respect to x, which is 2x, and then multiplying times lambda. Is that fair, everyone? No questions about that? Next one. 6 equals lambda times 2y. And then what's our last equation? The constraint, right? The constraint equation. All right. Now, there's some quick algebra that I can do just right off the bat. I can divide both sides by 2 here. So I could put 2 equals lambda times x. Here I could put 3 equals lambda times y. And then this one I'm just going to leave alone. So I've just kind of adjusted the equations a little bit. Those are my 3 equations. Now, you can't do what you just did a second ago. You remember a second ago we took the first equation and we moved everything over and we factored out and we got 2 solutions? That's not going to happen here. So, any ideas? Solve for what? You want to solve for lambda in the first equation and in the second equation, and then set them equal to each other. You could do that with one little catch. If you take the first equation, take equation 1, right, 2 lambda x, and, no, I don't know why I wrote that. 2 equals lambda x. If I solve for lambda, lambda would be 2 over x, but what did we just have to make sure? X can't be 0. All right? Let's not forget about that, because we do have to then go back and look at what happens if x is 0. All right, so I'm okay with that. This is all under maybe my first idea. Here's A. So I take equation 1, I solve it for lambda. How about equation 2? Solve it for lambda. So lambda is 3 over y, but y can't be 0. So what I'm saying right now in this thought is that lambda equals this and lambda equals this, so long as x and y are both not 0. Right? Okay. Now, if that's true, then I can say what? Okay, so I have a couple of options. I can set these equal to each other, can't I? Now, I heard plug into the third equation, but how would I? If you solved for x? Okay, that's another approach that we could use here. Right now, I'm going to set lambda equal to lambda, right? Set these two equal to each other. And what do we get?
2 over x.
We get 2 over x. So those two statements there imply that 2x equals 3 over y. And that means that 2y equals 3x. I'm just clearing out fractions here. Now what? How do you want me to use the third equation?
Solve for x.
Solve for x here. Solve for x here and plug it in there. Okay, so if I solve this for x, I would get, divide both sides by 3, I get 2/3 y equals x, right? So if we take, I'm just trying to recap, if we take equation 1 and guarantee that x isn't 0, and take equation 2 and guarantee that y isn't 0, then what we get is that the relationship between x and y would be that x is equal to 2/3 y. Now we can go to the third equation and substitute, replace x with 2/3 y, and we will have a single equation with a single variable, and we can solve for y. Once we know what y is, we can come back here and get x. once we know what x is and y is, we can come back and get lambda. All right. All right, so now, using equation 3, I know that x squared plus y squared is 13. I'm replacing x with 2/3 y. So 2/3 y, that quantity squared plus y squared equals 13. Let's go ahead and square that quantity up. 4/9 y squared plus y squared equals 13.
You'll get
Put those together.
13/9.
13/9. Common denominator, 13/9 y squared equals 13.
You divide it.
Divide by 13,
Get
multiply by 9. Y squared is 9. Y squared is 9. So y is equal to plus or minus 3. All right, any questions there? All right, do I know what x is now?
Yes.
Yes, because this is x, right? See, this is all within the same thought here. Okay? X is 2/3 of y. Now, y can be two different things, right?
Yes.
So I'm going to start writing these points down over here because I need to make sure they correspond. These are going to be my answers over here. I have x, y, and lambda. So I know that y can be, what, 3 or negative 3, right? 3 or negative 3. If y is 3, what's x?
2.
2. If y is negative 3, what's x? Negative 2. See, you cannot do this. This is a mistake students make. They'll say plus or minus 2, plus or minus 3. That is incorrect. This is 4 different answers, right? This is plus, plus, minus, minus, plus, minus, minus, plus. And the only possibilities are plus, plus, and minus, minus. So don't use this notation. It's not correct. All right, can we get the lambdas real quick? What if we go back to this lambda right here? If x is 2, then lambda is 1, right? And if x is negative 2, what's lambda? Negative 1. Okay, we've got 2 points so far. But all of this was done, right? All of this was done with the condition that x and y were both not 0. So now we need to consider that case, and that's going to be B. B. Suppose, I'll use this symbol for suppose. Suppose x is 0. What does that mean?
4 is equal to 0.
If x is 0, what can you tell me?
Y is equal to square root of 13.
Can it be 0?
No.
Why can't it be 0?
Because 4 does not equal 0.
Equation 1 can't be satisfied. Look, suppose x is 0, then equation 1 tells us what? 4 is equal to 0. And that's not true. Right? And in order for Lagrange multipliers method to work, you must satisfy all 3 equations simultaneously. I understand, and hopefully you see this too, that if x is 0 and you go to this equation, you're going to get 2 answers. But that does not mean these are critical points, because x being 0 does not satisfy the first equation. So we throw x out, right?
Yes.
So, nope. All right, suppose y is 0. Same thing, right? Then equation 2 means that 3 is equal to 0. That's not true. Okay, so nope, can't do that. Any other things that I can work with? When I was working under the whole thought process of A, I had just basically solved these both for lambda. I had worked with both of those, didn't I? Here, I didn't mess with this until later. That's okay, that's what we want. It's just, have we exhausted everything? That's really the only thing we need to consider, is have we exhausted everything?
We're doing 2 overlap.
First thing for equation 1, we can solve for x, and then we'll solve for lambda, set 1 and 2.
Okay, so let's do this. This is going to be a different approach, but it's going to give us the same exact result. And this is what you were suggesting the first time through, right? Okay, so I think I've covered everything, but let's go with a C, a thought process here, C. It's just a different way to get these same 2 points. What we have here is if I take equation 1, which was 2 equals lambda x, and instead of solving it for lambda, I solve it for x, then I'm going to get 2 over lambda equals x, right? But what are you promising me there? Lambda can't be 0, so I have to think about that, won't I? What if lambda was 0? All right. What would equation 2 give us if we solve it for y? 3 over lambda equals y. But lambda, again, can't be 0. But I already said that. So we're still good. Now, what would you do with that?
Use them in an equation.
Plug them into equation 3. This is x, this is y, right? So if I go to equation 3, replace x with 2 over lambda squared plus replace y with 3 over lambda squared. That must be equal to 13. And what happens when you square both of those?
You get 4 over lambda squared plus
4 over lambda squared plus 9 over lambda squared equals 13.
You add them together, which is 13 over lambda.
This is 13 over lambda squared equals 13. And then just multiply both sides by lambda squared. And you get 13 equals 13 lambda squared, which means lambda squared is 1. So this tells you lambda squared is 1, which means lambda is what? Plus or minus 1. We've already got those two covered, right? So how would you have gotten the x and y? Say we didn't do what we did first time. Let's say that this was our first thought. Then if you would have got lambdas plus or minus 1, what you would have done is come back in here and said, okay, let's say lambda is 1. Then x is what? 2, and y is 3, and you would have got that. And then you said, okay, what if lambda is negative 1? You would have got negative 2 and negative 3. Now, what if lambda was 0? Your first equation is what? 2 equals 0, 3 equals 0, you throw them out. So we're done. I mean, we did not have to do the C part, okay? But I'm just showing you there was a different approach. It's good to see the different approaches. All right, let's do another one. Oh, by the way, the picture of that, our original equation was a plane, and the constraint was a circle. So if we take our plane, we restrict it, there's our plane, we restrict it to that circle, and just plug those points in, we get that blue curve, and we just found the highest and lowest points on that blue curve.
Would this also work for the last question that you asked last class?
This will work for both the questions that we asked at the end of class. I know this seems like tedious. I get it. It is tedious. It's super powerful, though, all right? And we're only doing functions of 2 variables right now. I said earlier it works with basically functions of any number of variables. Because your gradient vector is always just the partials, and then you have lambda, which is a constant, times the gradient of the constraint. So. Okay, sorry, I was off in a different place right there. Here's what I was just thinking about. You actually did this in Calculus 1. You didn't realize you were doing it. If I go back to Cal 1 and I have a function of a single variable, y equals f of x, and I want to find the maximum of that, And what I'm going to do is I'm going to take and try and find where the derivative is 0, right? Okay, so let's say that we have a function of a single variable. What is the gradient of that? It's just its derivative. It's a vector with one component. So the gradient of f would just be equal to a single vector, which is just the derivative of f. Now, what would the constraint be? This is the part that is a little odd. The constraint is that your x values have to come from where? Anywhere on this number line? Right? The constraint, because x, your input is x, right? Your input's x, and if I'm constraining you to x is off this number line, what's the equation of the number line? Y equals 0, right? So my constraint equation would be y equals 0. And what's the gradient of that? If I call this thing my g function, the gradient is 0, so you're basically going to be setting the derivative equal to 0. Which is what we do, right? Okay, all right, sorry. Let's go back here. This one looks fun. 3 equations. 3 equations. First equation is you're taking the partial of f with respect to x. It would be y e to the xy equals derivative of this with respect to x, but don't forget times lambda. So how about 3 lambda x squared? Agreed? Derivative of that is 3x squared, but then times lambda. That's equation 1. How about equation 2? It's x e to the xy equals 3 lambda y squared. And then my final equation, equation 3. Oh, notice I'm not restricting, our constraint here is not a circle. Did you all notice that? X cubed plus y cubed, it's not a circle. Do y'all want to see this one first? Okay, yeah, sure. Yes, you do. There's the constraint. That's x cubed plus y cubed equals 16. If we plug that into this surface, which I won't show you the surface, right? Then where are the highest and lowest points?
I want us to kind of like think about how many points.
How many we're going to have? Okay.
We know ahead of time, like, oh, we're done.
Sounds fair?
Would you just solve for x and y?
Solve for x and y. Where? How?
Divide the x over y.
Which one are you talking about?
Well, equation 1.
You solve this for y. If you solve this for y, it's still in terms of y. Because you have e to the xy, you'll have y on this side also. Right?
Use logarithm.
Logarithms, ooh, you could solve for lambda.
Solve for each x, y, and both of them, and then set them.
So there's a lot of things here, right? I mean, I could solve this for lambda and set it equal, this one I can solve for lambda, right? So I could solve this for lambda, set them equal to each other. I could solve this for e to the xy, solve this for e to the xy, and set them equal to each other, right? Those are all great ideas. And yeah. I'm actually going to do it completely different though.
You can also divide.
So watch this. I'm going to take equation 1, okay? Now look, does everyone understand you could solve this for lambda?
Yes.
If you did, what would you have to be guaranteeing me though? X can't be 0 because you'd be dividing through by x squared. When you solve this for lambda, you have to promise me that y is not 0. That's fine. If you solve this for e to the xy, and this for e to the xy, you'd have to divide through with the x, right? And then again, you would have to guarantee me that x and y can't be 0. I'm just going to do something that, I mean, it's algebraically equivalent pretty much. I'm going to take equation 1, but I'm going to rewrite it. What did I do? I multiplied both sides by x. Now, why do you think I did that?
So you figure out what x cubed is.
I'm going to take this one right here, and I'm going to multiply both sides by y. And then won't I have xy e to the xy in here? If I multiply both sides by y, I'll have xy e to the xy. And then I can set them equal to each other. It's the same thing, okay? I'm just showing you that method because it's not as natural, and it's good to see it. So that's equation 1. Why did I put x can't be 0? Because when you multiply two sides of an equation, you can multiply by anything except 0. So I need to state that. All right, that's equation 1. Equation 2 becomes, this is all part of my process A, sorry, A. My equation 2, if I multiply both sides by y, I get xy e to the xy equals 3 lambda y cubed. And now I set these equal to each other, because look, they both have the same thing. So they're equal to each other. So that becomes 3 lambda x cubed equals 3 lambda y cubed. I know you might have the urgency here to divide lambda. Don't subtract. Subtract from both sides and factor. So 3 lambda x cubed minus 3 lambda y cubed equals 0. Factor out a 3 lambda, and you have x cubed minus y cubed in the inside. And now you set these both equal to 0. So here's what we've got. We've got 3 lambda equals 0, or x cubed minus y cubed equals 0, which means lambda is equal to 0, or x cubed is y cubed, right? Because I just move over. And if x cubed is y cubed, what can you tell me about x and y? They have to be the same. Because I can take the cube root on both sides. With cube root, you don't get the plus or minus. So these are guaranteed to both be identical. Make sense? All right. We have two different scenarios to follow here. You ready? I'm going to look at lambda being 0. Then I'm going to look at this. So if lambda is 0, what can we say? So if lambda is 0, what does the first equation say? If lambda is 0, then equation 1 tells us that y e to the xy must be 0. Agreed? What's wrong with that, though? Y can't be 0. Why can't y be 0? Because that's how we found this, right? We found this and we said, remember, don't let x be 0, don't let y be 0. And then what we're drawing a conclusion is that this is only going to work if y is 0, right? So what does that mean? Lambda can't be 0. Lambda being 0 doesn't work because it goes and we have to contradict ourselves. Understand? So this implies that y must be 0, but we can't, right? Can't do that. Can't let y be 0. This is all within the framework that x and y are both non-zero. So I'm going to chunk this. I don't need to worry about it. Now, what if x equals y? If x equals y, then what? I can rewrite the last equation. Equation 3 will tell me that what? You can replace the y with x or the x with y. It doesn't matter. I'm going to replace the y with x. X cubed plus x cubed equals 16. 2x cubed is 16. X is 8. X cubed is 8. X is 2. If x is 2, what's y? 2. Okay, here we go. I'm getting some answers now. If x is 2, x has to be y, so y is 2. And can we get lambda in this case?